Let me just first repeat for like 2 minutes, so just that we're still in the same picture. So this is the structure we're talking about. You should think of L positions here. On each position we have a standard, let's say pick a low density parity check codes. I've always typically taken as example a 361, but you could stick some other code in here. These are locally connected, so they're connected, let's say, to the nearest neighbors. But it's done in such a way that the degree distribution doesn't change. So locally, the degree distribution is exactly whatever you've started with. But there are effects at the boundary. Okay, so we have two parameters, the L, we're having the W with how the connection width is, and then we're having how many nodes there are. And just as a reminder, maybe think of this as whatever, 10 or maybe 20, this is maybe 2 or 3, and this should be larger, okay? And I'll talk about how large this should be. But there's some effect at the boundary. At the boundary, we're having more of these check nodes. So we're having extra check nodes here, and this will be one important topic today. And due to this boundary effect, what we have is if we're running this decoder, and so this is the local probability of error that we're having. If we're running below BP, it's basically the same picture that we have. These steps are exactly what the standard uncoupled code would do. And there's a little bit some effect at the boundary. But what's nice is if we are going above the BP threshold of the uncoupled case, then we see something nice. Indeed, in the middle, it will get stuck exactly in the fixed point that we had talked about, that the uncoupled code would get stuck. But globally, the code is not stuck because at the boundary, we have more knowledge. The boundary nodes can help the nearest neighbors to the right. They themselves can then decode, et cetera, et cetera. And so you should really think of a wave that moves at constant speed inside. And since we started the wave at both sides, it moves from both sides in. And so that's really the effect that's happening for spatial coupling. And then if we go above this special point here, denoted already as map threshold, so this will turn out the map threshold of the underlying code. Then, of course, we cannot hope really to decode. It turns out that these two codes, the uncoupled and coupled one, have the same threshold, not just the same BP threshold, but the same, so not just the same threshold decoding, but they have also the same map threshold. So the map threshold of this code is not better than the map threshold of the underlying one. Then in this case, you get stuck. Doesn't matter if you do BP or if you do map. But at the boundary, you will still decode a few just because you have some more knowledge there. Okay, so this is roughly as far as we got yesterday. And we said that this is really the same effect that also happens in many other physical phenomena. So we mentioned in particular this nucleation effect. So this is supercooled water, but you can also think of, for example, crystallization. You can think of simply a liquid that will crystallize, and you need to get it started some seed, or you need some energy, or we've seen in the heat packs, there's sometimes some other mechanism to get it started. And once it gets started, you see it goes down at constant speed, and that's exactly the same as the wave happens here. And you can actually then try to compute also from physical considerations how fast the speed goes, etc. Okay, so this is this metastability and the nucleation process. Good. So now, how well do these things do? So let's look at a few channels here, and I stick right now for capacity I have. Of course, nothing has to do with this particular capacity here. So let me just pick three random representatives of channels: the binary ratio channel, Gaussian channel, and the binary symmetric channel. And so if we stick with this 3.6, which is kind of the first non-trivial code of rate a half, which is regular, then remember we had here 43% if this was decoded in an uncoupled way, but it jumps to close to 49% if we allow this coupling. So that's quite an improvement, and recall that the capacity for this would be a half. Okay, so this is already fairly close to a half. Now, what about for the binary added by Gaussian noise channel? Also here we have quite some jump. It doesn't jump quite as high, but about 48. Again, this is normalized so that a half is the capacity. And for the BSC, and that's characteristic, the BSC is kind of the most difficult channel, and that appears in many, you can see this in many instances, also in analysis of polar codes and many other ones, that BSC is typically kind of the most, if you fix the capacity of the channel, it's kind of the most difficult one to get close to, particularly if you fix a certain length. Okay, so it's not so even here asymptotic, it's not super surprising that gives you the worst. But what happens if you go up? Okay, remember, when I showed you that if you take the uncoupled case, right, and I'm simply increasing the degrees, the threshold in general, okay, it's not always that it strictly goes down, but eventually the threshold will go down. In particular for this case, the threshold strictly goes down, right? We have seen that, for example, for the 3.6, if I went 3.6 to 4.8, instead of the 43% that I usually had down here, only 38% or something if I do the uncoupled case. Nevertheless, for the coupled one, it's very different, right? It actually goes up, right? And this is already now very, very close to capacity. And also for all of those, it goes up, right? And so you can go up further. And you can see that you don't really need to go to enormously high degrees, right, to approach it, because anyway, we'll talk about there will be other effects, right? In particular, something like the finite length effect, how fast the code approaches capacity. You never do deal with an infinite code, so it's basically meaningless already to look at the 5th digit here and try to improve that. Okay, there are much other effects that are much more important. But what is very nice, you can see that they all approach it. And indeed, one can show that this is universal, okay? So you can give a lower bound on how quickly they approach capacity. And so that's for any binary input memoryless output symmetric channel, okay? We saw 3 examples. And so the rate that you can achieve at which reliable transmission can happen is always lower bounded by, this is the actually the design rate, okay? So this is basically, think of this here as the capacity, and then there's a small penalty. And this small penalty, forget about these terms. Essentially, what's important is depends on the left and right degrees, but you can see it's exponential. There's a minus here, all the rest is positive. And in the degrees, it will exponentially fast go to 0. Okay, so this penalty term will go to 0 relatively quickly with some constant here, and that's not necessarily the best expression you can give. But this tells you that you don't have to go to enormously high degrees, and it also tells you that this is universal. Okay, one and the same code will work for any of these channels, and that's one of the nice properties of spatially coupled ones. Something that, for example, polar codes in their standard incarnation don't have. You can try to come up with other constructions that the code actually does not depend on the channel. Okay, so let's quickly summarize here. So what we have seen so far, we haven't seen why, but if I take a standard ensemble, an uncoupled one, I couple it, and then I do standard BP with proper termination, then what I should expect is that the threshold should be actually as good as the map threshold of the underlying code. Okay, so that's quite nice. Now, since it also turns out that the map threshold of this coupled codes is also equal to this. Okay, you basically now under BP go to the highest possible threshold that you can achieve, and that's why we talk about here this threshold saturation, and that's something that makes more sense. I think once you have looked at, there's a lot of literature in statistical physics that talks about various thresholds that systems can have. And so there are fundamental thresholds like the map thresholds, but there are many other thresholds that have to do with the dynamic of behavior and how systems change. And so this simply means that this threshold, all these thresholds that you have in this system, they all go to the same threshold, namely the map threshold. It's not just the dynamical threshold that I'm talking about here. And as I mentioned, things are universal. That's also quite nice to have. But there was one downside that we already mentioned, right? We pay a price, and the price was that at the boundary we have to terminate. Okay, and so one of the topics right now that we'll talk about is a little bit to see, how much might this be, and also, not everything is known there. There actually is quite some nice open problems there if someone is looking for them. Okay, so let me come back to this, and let me first get a little bit to, how this all developed. So some of you might know this paper. There was Fellstrom and Tsigangarov. This was in 1999, and they had a class of code they called convolutional LDBC codes. And these are essentially the structure that I'm talking about here. The connections that I'm talking about here were different. They were done in a convolutional manner. But the type you do the connection doesn't really make much difference. So the only thing that they didn't have at that point is they didn't have the termination. Okay? And so basically think of it as like the circular ensemble, right? So you can do this ensemble, but if you don't terminate this ensemble, then you don't see this effect. Okay? So they had exactly this code. But at that point, there was also no reason to believe that something like this should happen. But they didn't have determination, and so because determination was missing, the codes behaved essentially exactly the same as the underlying codes that there were. Okay, so there might have been maybe some other reasons why you might want to do it, this didn't really change. Okay, and then there were, there are lots and lots, and by now there are quite a few papers, and I'll mention it later on some more. And specifically, I don't want to mention the specific names, but you can read them. Lots of people that analyze this type of code. So what are typical ways you can analyze them? Weight distributions, maybe stopping set distributions, if you ever heard of that. Various properties that this code could have, maybe how to encode them in an efficient manner, etc., etc. Okay, so there were quite some paper by a set of people that you see now here, and various variations appearing. Now, something that then was quite important, and so this was particularly a set of people around the group of Dan Costello, was this paper here. And so what happened is there that in the, I think in some previous papers here, people started suddenly, number one, to have some termination in there, okay? And number two, so they first terminated them in some way, and they simulated these codes, and they saw that these codes actually work quite well. And so what they then did too is to run dense evolution to figure out thresholds. Okay, and so these were quite good thresholds, and some of these thresholds you see here. And so I remember that in 2003, I think I visited Dan. He said, "Oh, there are some very good codes. There are very good thresholds." But at that point, I must say I didn't really pay much attention, because there are quite a few different codes around that have good thresholds. In addition. Unfortunately, I think they called them convolutional LDPC codes. And if you know anything about convolutional codes, the thing that defines them is that the initial state, is forgotten very quickly within the coding process, right? So, if you hear that, it just primes you to think that this cannot possibly persist through the decoding process as the length grows on. Okay, so kind of the name already implies that there couldn't possibly be any effect, because convolutional codes, if you ever tried a convolutional code, of whatever, some state, and you run the Viterbi algorithm, you know that it basically doesn't matter what the initial state that you give to the code, right? Which is exactly the opposite what happens here, where the initial state is exactly what drives this performance here, right? And the reason, this kind of confusion is this, that in this case, the state that we're dealing with is gigantic, okay? Because it's basically 2 to the size of the number of variable nodes we have, okay? Which is much, much larger than, of course, for any code that we typically deal with convolutional codes, okay? Okay, but so they did essentially these, these thresholds, and came up that they have some very good thresholds. And so what happened was that Cyril Meillasson, and then together with Andrea and also with Tom, in Cyril's thesis, which, and I'll get back to it, he had looked at a long time ago, so that's quite some years ago, he had looked at something that was called the Maxwell construction. And in particular, what our aim was is trying to figure out what the map threshold of these uncoupled codes would be. Okay, so we just said, okay, fine, you can do BP, decoding of a 3.6 code, but what if you actually could do map decoding of the 3.6 code? What would the threshold be? Okay, and it turns out that these are quite, so finding out these fundamental thresholds is actually quite a difficult problem. But Cyril, managed, at least for some codes, so particularly for the class for the BEC, together with this Maxwell construction, I'll tell you a little bit what it is later on, to determine some of these thresholds. And these thresholds were also at least upper bounds on the map threshold for general channels. So for the BC, we could prove in many instances that were indeed map thresholds. And so what happened is that then, when at some point, we looked at this paper, and this was then together with Srinivas, who is like here, and also Tom, we looked at the papers by, that gave these dense evolution things and the thresholds. We realized that these thresholds are actually exactly the same thresholds that we had already computed beforehand for the underlying code. Okay, so originally when we computed the thresholds for the uncoupled codes, there wasn't really super much motivation for it, because in general you cannot decode a code up to the map threshold, because in general it's exponentially complex, right? But it was just interesting to see. For example, if you're not close to capacity, to figure out, well, how much of this is due to the algorithm and how much is due to the actual code, right? So you can kind of cleanly separate these things out. So that was our motivation. But it turned out that because we knew these numbers, and then we saw these numbers, it became apparent that something interesting must have been happening, because these were exactly the PP thresholds for this coupled thing were exactly the map threshold. And so there was actually another person that realized this. Is Gianluca Luigi, who is at the German DLR, I forgot now what it actually stands, the Deutsches DRL, maybe Deutsches. Okay, I forgot. Okay, so it's a German space, a company, and he had also at some point looked at these thresholds, and I guess he was in some physics defense that he told me about, and he actually also realized that these two things must actually be the same, and that led then to some further paper by where also Ben Costello were in there, where they also observed this observation. Okay, and so what we were then able together with Srinivas to prove that indeed this was in this paper, that indeed first for the BEC and then for general channels, that indeed that's what's happening. You have exactly these thresholds are exactly the same. They are universal, and so you can actually achieve capacity with this. Okay, so this was a little bit the story, and if you're interested in, of course, transaction information theory or archive, typically archive has, it's the best source because papers are much earlier there than what you would find. And I think, at least in this area, I think in general, in the information theory area, we have actually a very good coverage of the articles that are there. Okay, so it's a much better way, and it's also very easily accessible. Okay, so now so much to the history. Now let's get back to some of the practical considerations that I talked about. So let's first look at the rate loss in here, and so there's still some, I think, very nice and fundamental open questions in here. So let's look again at this particular example. We have this 3,6, and as we said, right, if I just move the middle part to the right, then it's even clearer what the rate loss is, right? So this is a 3,6 one. I'm looking at the protograph one, and since this has degree 3, one will go to its own position, one will go to the right, and one will go 2 positions to the right. And because we have this here we have exactly 1 check for 2 variable nodes, but here we have 2 extra check nodes on the right? And because of that, every check node we have in addition is 1 degree of freedom that we lose, right? And so because we lose that, well, how many, and of course, if I now go, let's say, to the 4,8 instead of 3,6, right, then I have actually, 3 positions that I lose. So the number of positions that's sticking out here will be this degree minus 1, right? Okay, so if you're thinking of this, then it looks like that the rate loss will be what? Well, we have so many variable nodes, okay? So this is the chain length here, and then, depends on how many checks versus variables, so that's the ratio of check to variable nodes here. And so I have so many of those, and then how many extra check nodes I have? Well, I have this L, but then I have this extra DL minus 1 check nodes here. And so if we remember the formula was just the total degrees of freedom I have minus the degrees of freedom taken away divided by the total number of freedoms I have. And if you figure this out, then you will see that the rate will be just, the usual rate, the design rate, but then we have a penalty, okay? And so the important fact is that this goes down like 1 over L, the chain length here, but there's something extra in here. This is just this conversion rate, but the important fact is here the DL minus 1, right? It looks like I have an extra DL minus 1 degrees of freedom that I lose, right? And so if it's like this, then, okay, so what this would mean is it's not a problem if L goes to infinity, but as I'll talk a little bit more later on, the total block length is, of course, not just the L, but it's the L times how many variables I have in here, okay? And I can't have, if I want to have good performance, I can't have too few variables in this position either, because then something else comes in that's called finite length scaling. So I have now 2 potential losses that appear here, right? One is the potential rate loss that I have here, and the other one is the loss if I don't make one of these sizes large enough, okay? And so on the one hand, I would like to make the L very large, okay? On the other hand, I would like to make the n very large, but the product L times m, which is the block length, is fixed, right? That's my requirement. I cannot go too large, okay? So the question is, how should I treat this one? Okay, well, you can do, so a naive, if you think of a naive physics thing, it's that, to get this process started, okay, depending on the degree, well, if you have a small ball, then maybe you just have to give it a small push, okay? But if you have a larger ball here, then, so you can think of that you have to actually give it a larger push, and so you have more loss, okay? You have to initially get it started. Once the ball is rolling at constant speed, the process will take over. Okay, but it turns out that it's not quite as bad, okay? So why is it not quite as bad? Well, the first thing is you can do something trivial. We don't need that this process necessarily starts at both ends, right? So the way it is right now is that this is exactly the same as this. I just, I just drew it that it's not symmetric. But basically, I have now a wave coming from both sides, right? Okay, I don't necessarily need that the wave starts from both sides. What is if it's enough that the wave just starts from one side and then sweeps over it, okay? I mean, there's no reason I have to start decoding on both sides, sorry, okay? And so if you do this, then what you can do here is then you can just combine these nodes here such that the degrees should be exactly the same here. So you can make them all degree 6 nodes. and then this will still work, okay? So that would work fine. And if you figure out, how many you need, then you will see that now the number of extra check nodes you need is halved, okay? And you can kind of see why. So every time the degree goes up by 1, and so you basically just need half really the check nodes if you make them full degrees. So this means that now the rate loss, at least we have a factor 2 in here, okay? Better, but still you have, unfortunately, this annoying factor dl minus 1 in here. And then there was a nice, a nice idea by Kenta Kasai. And so what he said is the following, okay, well, if we have these extra nodes here, one thing we can do is we can just actually delete these extra things sticking out and only keep a single extra one here. And he then ran dense evolution and showed that, for all the cases he tried, that works. Okay, so and indeed it works. But that's, for example, the first open problem. I don't think we have a proof that indeed that actually always works, right? So here at the left side, there's no problem. The wave will get started. But of course, it could be that potentially at the very end, there might be some trouble, right? We have taken out now some extra degrees of freedom. And it's not clear a priori that this will work, right? I mean, clearly, if I delete that too, then clearly at some point I must be in trouble, right? I mean, I cannot gain something for nothing. But it does work. But one I think nice, interesting problem would be to see exactly, how to do actually determination on the right and how much extra degree of freedom I actually need. But at least for all the examples he tried, and you can just try this out after all. Anyway, when you design the code, you can first try out if it works or not. Then you just need now 1 extra degree of freedom. If you now just need 1 extra degree of freedom, you still have a loss here. It still goes down like 1 over L, but you no longer have the this extra dependency on the degree in there. Okay, so that's already much better. Okay, so it doesn't matter if you take a 3.6 or 4.8 or 5.10, you still have only 1 degree of freedom that you lose. Okay, and as I said, if you're looking for a nice problem, I think that's one, trying to prove what's the best you can get away with. Okay? So now the question is, how can it be, right? How can we actually get rid of it? And so the idea is that a better analogy is still one where you push a ball, but the point is that once the ball gets started, okay, you don't need that the ball actually runs at constant speed throughout the whole decoding process, right? So you get started, you need to actually push it and need to give it something, and this will be more depending, how big the ball is. But the point is, at the very end of the decoding process, you don't need that the ball still runs through the chain and falls off the cliff, okay? You just need it that it just arrives to the end. Just think of momentum, and you can actually get some momentum out, okay? So what does momentum mean for us? It's information, okay? So just think about how the structure of the code is. Think of this code that has a very nice protograph structure, right? So what will happen is that you will have nodes, and these nodes, so if you think of a check node, then, and think of the protograph, and let me now just do maybe 3 such edges here. And let's assume the wave comes from here, right? So, how, in what sense, so just think also of the BEC, because then it's easiest to think about it. So we think of the BEC channel. Now, if a code is very good and very close to capacity, what must happen is that every check node exactly determines 1 undetermined bit, okay? So this cannot be that two check nodes determine the same undecoded bit, or that 1 check node doesn't determine an undecoded bit, because any check node that doesn't have 1 bit to be decoded is a waste, okay? That bounces you away from capacity. So it must be that if you're very close to capacity, every check node exactly determines 1 bit. So the question is now, if this check node has degree 3, the node arrives from here, which of these bits will it determine? Okay, it could determine this bit, or this bit here, right? And so now, let's assume we have only a one-sided case where the wave only arrives from here. So at the beginning, a lot of these things are not known. Then it's most likely that this edge will be the first one that's actually going to be known. Okay, so that there will be a known message running from here. Is that clear? Because these bits to the left are most likely known to be first, right? And then the second most likely that will be known at time will be this. And as soon as all except one of the edges are known, okay, what will happen is that this XOR will now determine the value of the bit that's connected here. Clear? Now it could have happened, of course, and once in a while it will, that this edge is known first, okay, and maybe this edge is known, and then it's actually this bit that will get known, okay? But it's more likely that the messages go from left to right, okay? Now, if I have a chain, and this chain goes on forever, and I'm thinking of a cut here, right? And I'm thinking of now edges going along this cut, right? So there will be edges going from left to right or right to left. Then what in the decoding process happens is that it's more often that the edges, determine a bit to the right rather than something that determines something going backwards. That's just in the nature of the decoder, right? Now, if I'm going through and I still have to continue, I need this. That's exactly the process that will help me to continue to decode, right? But if I'm actually terminating the code at this point here, right? So if actually at this point the code is over, then I don't need actually these messages going from the left to the right. Clear? I mean, it's just a waste. There's nothing else that I have to determine here, right? And so because of that, I can actually at that point locally get rid of some of the checks because I actually don't need them. Okay, so that's the reason why something like this can work and why you can basically extract again some information out of this process and not get not have this. But currently, and that's the second, and that's perhaps one of the most important open problems. Currently, there's no fundamental bound that tells us how much rate loss at the end we should have. Okay, so currently it's not even clear whether or not you actually at the end need any rate loss. Right? It might be that at the beginning you have to push it, but perhaps you can extract everything again at the end. Okay, is there any fundamental bound? And so in physics, right, there are such type of bounds, right? So at least to get things started, there are bounds. And so what we're looking is essentially for something for the equivalent. So imagine you want to grow a crystal, okay, and you have some saline solution in there, and now you have a small seed in here, and you're asking, the seed has already the crystalline structure that you want, and you're asking whether or not the seed will now start growing, okay, or perhaps it doesn't start growing. And so what are the considerations that you can figure out how large a seed you need? Is this enough, or do you need maybe a seed of this size? Okay, so what do you need? So there's some very clear rules of how you can determine that, at least in principle, and the idea is the following. So take a seed, and let's assume the seed has radius r, right? And so now ask yourself the question, is it from an energetic point of view better if the crystal grows or if the crystal perhaps even collapses again? What is better for the system, for the global energy consideration? So let's assume hypothetically we would grow out, or the system would grow out the seed further, okay? So then we have here a certain volume. Okay, and so this extra volume, what will happen in the extra volume? Well, in this extra volume beforehand, this was in this non-stable, this pseudo-stable state, okay, beforehand. So it had higher energy, and once it becomes a crystal, it will actually have a smaller energy, right? So whatever this volume here is here, this delta volume, this times some delta epsilon, okay, where this delta here is the difference between the energy states. That's what you will do better, okay? So the system will be now in lower energy by this amount, okay? And how does volume grow? Well, volume goes like the r to the third in general, right? So there will be an r to the third term here. Okay, so on the other hand, there is a surface here, right? So you have a surface around here. And here, the mechanism is perhaps not so clear, but if you have if you have a material that's in two different states, there's an interface. It's exactly the boundary between the two. And there's some energy associated to this interface, okay? It costs some energy to have an interface, and that's proportional to the area, okay? So there will be another term, okay? Let me say minus. And this will be, in terms of the r, proportional to r squared, because we're talking about now the surface. And so this will be some r squared, and there will be some other term. So this is delta, let's say the area here, and then there will be some other term, I don't know, let me call it d, okay? And this has to do with the interface energy that you have here. Now the point is here that these constants, of course, this one and this one might depend on the material, but the point will be that this is r third and this is r squared. So clearly there will be eventually a term, eventually an r, for which the left term here will be larger than the right term here. Is it clear? Yes?
Is that the difference that you are saying that is proportional to r squared or r squared?
I'm talking about the whole one here. This was the difference, and here it will then be the whole energy that you have in the system. Okay. Otherwise, if you want to, I could say that this would be this squared times delta, and then do this. Okay. So, but still the difference is the r, so it's not going to make a difference in the calculation. Yeah. Okay, so eventually it's clear that there will be a term where these two things, as a function of r, will be equal, right? And that's exactly the minimum size of the seed that you need to get it started. And so the question is, if there's something, so we have essentially two problems. The question is, how much do we need to put in on the left to get it started? And that would be exactly this question that we have here, okay? Except that we don't have exactly calculations like that, okay? What's the equivalence of, the surface that we extend? What's the equivalent of, the volume, the energy state that we extend, okay? So it would be nice to come up with something that's fundamental and tells us, no matter what you do, you will have to give it a push of that size, and a push means so many degrees of freedom that you will lose, okay? But then on the right-hand side, I don't know what's the equivalent here in the crystal growth is, on the right-hand side we can actually get things back out, okay? And so there we have some bounds and so on, but also I don't think that they're necessarily the right bounds. And the question is, are these bounds in such a way that is it clear that you have to put always more in than you get out? Or perhaps these things do even cancel, right? So I think it's a nice fundamental question about systems like this, but it's also something that's eminently practical, right? Because essentially the biggest thing that bounces away from capacity or for finite lengths is exactly this term, okay? And if you can make this smaller, even just a factor 2 or whatever, this will have clear practical implications on what you can do. Okay, now one thing that's quite related to this is actually the encoding question. Okay, so I'm not going to give you a general thing of how you encode it, but let me just show you why this might actually be quite related. Because there's at least one mode in which you can use these codes in which there's actually no question of rate loss, in which you have essentially no rate loss. And what is this mode here? So let's just look again for this very simple 3/6 code, and let's think of the following. Let's assume I start here, and let's think of these as the information bits, and let's think of this as simply extending to infinity. Okay, I just taken an infinite string. So let me think of this this is the information bits, and let me think of this as the parity bits here. Okay. So let's assume I just fill in here, these are maybe 1,000 bits here, and I filled in just random information in here, right? Okay, I can do this. Now, so far I haven't violated any constraints here, but now I better make sure that in order to fulfill this, right, which has only degree, it's...
Here, I sort of feel for this example. So you start stress process, you keep going. Here, do you expect surface tension to come only from the right extreme, or do you expect surface tension?
So I can just be a little bit louder.
Do you expect the surface tension to come only from the right extreme, or throughout the medium?
Do I expect the surface
tension, the delta A term?
No, okay, so what I was talking about, this part here, just has to do with the beginning of the process.
But you want to equalize because you want to stop at the end. You want to stop without...
Yeah, this picture has nothing to do with what happens.
Yeah, but the intuition, just with the intuition. So you want to remove some check notes back then. That's probably going to create some stopping condition.
Right.
And so do you expect that to similar, like, increase surface tension, right? Do you expect the surface tension at least like there, or you just see something other, like, what is the intuition?
You mean how much of this I can potentially remove? You think that we can remove something like this term? That's what you're talking about?
Yes, is that the
I don't know if the two are related. It's not clear to me. Okay. So we can maybe take this off, and you can do some bounds by figuring out how much of the information goes left to right and right to left, and you can compute these bounds. Okay. And they are somewhat better than what this one that I showed you before and so on, but it's not clear to me that that's a fundamental bound. Okay, and that's the best we know. Good. So let's get back. I put in information in here, and now in order to still fulfill this constraint, whatever, if this bit here is connected to a particular check node here, then whatever the other bit is that's connected to the same check node, I better set it such that, basically this is a repetition of this, right? Because I need to fulfill this. But what you can see is that I can fill in any information I want here. Think of an infinite stream. And then I can always do this one here to just fulfill, this will have inductions here, and then I just always use this one to fulfill this constraint up here. Is that clear? Okay? And so as long as I'm going on forever and never stop, I will never get in trouble. Okay? I have always in the next position one check, one bit that I can fix to fulfill all the constraints. So what this means is that I can actually think in such a case as this whole thing here is being my basic block length, okay? It's just one of these sizes, my basic block length, and I can basically always shift them in, okay? Put in the bits, I just take a block, whatever, let's assume there are m bits here. This is my m bits, I'll put some other extra m bits here, and this 2 m bits is now actually my fundamental block length that I have, okay? I can just encode like in this way and think of that is the block length. And I'll show you now in a second that the decoding can also be done in this, in a windowed fashion, so that you don't need the whole code to decode, you just need a few bits here. And so if you go in this manner, right, then once you have started the process will simply continue, okay? And it will simply go on, and now you have, since this can be very long now, the L, because that's not really what defines our block length, essentially I have no wrinkles, okay? Now of course there's one small issue, and the small issue is that eventually it can happen that no matter how well it's designed, that the channel is very atypical, it behaves in a very atypical fashion, and then it could happen that at some point, somewhere in between, you get stuck, right? You have a decoding error. And so you have to have a mechanism to restart it, okay? So you cannot make this too long, right? Because eventually, even if it's after 1 million or 1 billion of these positions that you decode, eventually you will get stuck, right? And so you have to have a mechanism to recover from this. But if this mechanism could be on a much larger scale, then this is typically what you have to deal with block codes. And so in this sense, you might actually get rid of the rate loss problem, okay? But not all applications probably will be okay with such a thing. Some applications it's probably okay to do this. Perhaps some other application it's not okay to do something like this. And you want really the whole thing to be the block length, and then you need to deal with the rate loss itself, okay? Good. Now, since already insulted once people, okay, let me show you can do it again, okay? So when you yes.
Sorry, just so then encoding is easy.
So so this depends now a lot on the structure, right? So if you have, for example, a structure like this in a protograph, then it's you can certainly encode the whole part up to at the very end. You might have to solve still a system of equation, and there you might still you might have to reconfigure the code a little bit such that then encoding is still easy. Okay, so the whole part it will be easy, and at the very end you probably have to slightly change your structure such that you don't have to solve a linear system of equations. Okay, it would still be a linear system of equation of smaller size, but it's better if you could avoid that altogether. And you can do it in the same way as for LDBC codes. People have found out slight variations on the code so that the encoding is easy. Okay, it can be done, but needs thought. Okay, needs thought, and of course interacts with other things. You make sure that the performance doesn't suffer, etc., etc. Okay, good. So now, one of the oldest and most fundamental ways of how to analyze a code and how to say that a code is good is what's called error exponent, right? And I hope we have all, you all know what that is, right? What is it? So you have a code, you have, what are the basic parameters you have in a code? You have the block length, right? And then you have, let's say, the channel parameter, the rate at which you want to transmit. You have, of course, also the capacity where you are, okay? And then you have the probability of error. And so you would like to relate how these quantities, behave, right? So you're not thinking of just a single code, you're thinking of family of codes, so you're having various n. And so the error exponent is something in which, what do you do? Well, so this is a family of codes of increasing n here. And so the error exponent is something in which you basically take a cut down here, okay? And you're looking at how the error probability decays as a function of the block length. Okay, so you do this. So this is, let's say, somewhere here is the threshold. Let's assume this is capacity here. You're a little bit away from capacity. You make a cut here, and you're looking where does this cut these various curves that you have here. And so when you go down, right? So as you increase the block length, then you look at how the error probability decays as a function of the block length. Clear? So the rate is fixed. Okay, the channel is fixed. And now you increase the block length, and you're checking how the probability of error decays, right? And so you hopefully have heard that the best thing you can do is some exponential decay, right? So you can make sure that the error probability goes down, and the way it will decay will be something like e to the minus, okay, the block length, and then there's an error exponent, and rather than writing down the error exponent, let me write down the gap to capacity, so the difference that you are away from capacity, and let me be already close to capacity, then the behavior of this is something like delta squared. So delta is gap to capacity. So in general, this whatever I have here is called the error exponent, and it's a function that's not known in the whole region. There's still some some open questions, but in particular, close to the capacity, this function behaves like delta squared. Okay, so that's fine. So that's a, it's of course a very nice parameter. It's something that has played an important role in the development of coding. But I claim that from an engineering perspective, it's not actually the parameter that you want to look at. Okay, so what I would like you to encourage is whenever you see a code and so on, and someone tells you Eric's point, you say, okay, so of course you can compute it, it's nice and everything, okay? But I think there's a parameter that's actually much, much more important to compute from an engineering perspective. And let me call it the scaling exponent or the scaling of it. And let me try to explain why I think it's more important, why I would like to encourage you to look more at that. Okay, so we're looking again exactly at the same parameters here, okay? But now what we do is we do something slightly different. Instead of taking a vertical cut, okay, a revolution, we take a horizontal cut, okay? Amazing, okay? And the next thing, you'll take a 45-degree cut, okay? Okay, so, but why is that, so what does this mean now? Okay, so I take a horizontal cut here. And what I will measure now, what I'm interested in is that, in the limit, okay, somewhere there's a threshold here, okay? So in the limit, you should think of that these codes will be a box, okay? So in the limit, the behavior of the code will be a box. It will be 0 here, the probability of error, and it will be 1 here if I'm talking about block probability of error. And so what we will measure is basically this distance here from the point here. So this is a function of n, and there will be a distance to the actual threshold, okay? So perhaps I have a slightly better plot here. So this is again the same figure here. So these are now many more, a whole family of such codes, increasing n. So as n, it's just unfortunately flipped. So this is the threshold here. This is the block length, okay? This is the probability of error. And so now as the block length increases, I'm getting closer and closer to a step function here, right? Now, it turns out that when you're looking, and so what you're interested in is that you're interested in is exactly in this gap to capacity as a function of n. So you're fixing a particular probability of error. You're taking the horizontal line here, okay, whatever this probability of error is, and you're measuring how fast these points as a function of n approach 0 here, right? Approach the threshold. So that's this finite length scaling. Now, it turns out that, for at least in our cases, when we talk about coding, that the way this is that the scaling, okay, so the first order term, so think of it as like in a Taylor series. I'm not saying that this is exactly like this, but up to higher order terms, this behaves like n to the, okay, and it's just written, unfortunately, for historical reasons, n to the -1 over mu. So it behaves like some power of n, okay? And so what power should you think of? Well, optimum codes, I'll get to it a little bit later, they actually behave like 1 over square root of n. So this gap here for optimum codes goes down like 1 over square root of n, okay? And so in this case, the mu would be 2, okay? And so that's the best thing you can do. And so, of course, what you would like is that you would like this mu to be as small as possible, okay? So we can just see if I do a different mu's, right, and I see what this means, then you can see that the smaller the mu is, of course, the faster these things approach, right? So you would like to have something where this mu is as small as possible, okay? Ideally, we could go down like 1 over n, right, would be even better, right? Clear? You don't want it like 1 over square root of n. Okay, and so different codes will have different values. So the optimum codes will have 2. If you think, for example, of polar codes that you have heard, the value is around 4, okay? Something between 3.6 and 4 point something, okay? So for polar codes, this value is unfortunately about roughly twice, twice what it should be according to the optimum thing. And this means that asymptotically, you need roughly the square of the block length to get to a certain gap, okay? Of course, we ignored all the constants and so on, okay? So that doesn't necessarily mean that a code of length 1,000, you can just follow this because there are constants in front and higher order terms, but it tells you still that, how quickly things will approach, and eventually, if you look at large enough block lengths, this will matter, okay? This constant does matter. It's not the only thing. Okay, so now, let me just, just in case you haven't seen, let me just tell you that, that 2 is the best exponent is kind of a triviality, okay? This simply comes from the variations of the channel, and that's very easy to see. And so how do you see this? So let's imagine, so let's first think of a coding perspective. Let's imagine kind of the best code we could think of. And what could be the best code? Okay, the best code could be is that the code has, this is the channel parameter here. Let's assume it's the epsilon, the erasure probability. And so somewhere here we're operating at an epsilon which is 1 minus r. So this is exactly capacity. We're operating exactly capacity. And so, kind of the best thing we could hope for is that we perfectly, get everything right here, okay? But that then actually jumps, and then up there we can't do anything, okay? So you could ask, okay, could it maybe even be better? Could it actually be that we perfectly do everything here, and then maybe here it just slowly goes up, okay? Turns out that you can actually not have that, okay? So we'll talk about this later on. Kind of these areas that you have here are fixed, and you can only decide where to put this area, okay? So you could decide that this slope was a little bit like this, but then this would cut like a 45-degree line, okay? So let's assume that the code behaves like this, that as long as I receive a certain number, as long as I receive at least as many degrees of freedom as the code has, right? The code has rate R, so I need at least R observations. Otherwise, I cannot hope to uniquely decode the code right? Binary ratio channel. I mean, if you have a file, and the file has, let's say, 50% redundancy, but I get only 40% of the observation, I cannot possibly hope to restore that file, right? So I need at least 50% of the file to restore. And the miracle of coding is that it doesn't matter which 50% you get, you can actually do it, right? So that's the nice thing. Okay, but now let's look at the channel, right? The channel is just, let's see, the binary ratio channel with parameter epsilon. Well, let's assume I'm transmitting, just a little bit below here, or whatever I'm transmitting. Well, how many erasures? So there's a slight unfortunately thing that this is the expectation. This is the number of erasures that I have. Well, how many erasures do I expect? Well, n, the block length, times epsilon, right? That's the expected value. But of course, this is a finite length. This is a binomial distribution. So of course, I will also have a variance term on top, right? I will not always get exactly n times epsilon. I will sometimes get a few more, sometimes a few less. And the variance, right? I think you have seen that, right? That the variance will be n times epsilon times 1 minus epsilon. So this means that the standard deviation is just the square root of this, right? And so if you're thinking of now this binomial distribution as a Gaussian here, right? Then this Gaussian will have a mean, let's say epsilon, but this Gaussian will also have a standard deviation, and this standard deviation will be the square root of this. Okay, so this number of erasures you can think of as a Gaussian with this mean and this variance that you have. Clear? So now what of course can happen is that even if you're transmitting somewhere close, there will be the tail of the Gaussian that will end up on the wrong side of the curve, right? So if you're ending up that the total number of erasures is more than this n times 1 minus r, n times epsilon, then because of the assumptions we made here, you will make a mistake. Clear? And so of course, how many mistakes will you make? Well, it's very easy, right? It's just whatever this Q function, it's just the Q function, whatever the tail of the Gaussian you hit away, and that's typically expressed as the Q function. So it will just be the Q function of this difference here, which is this one here, right, divided, normalized by the standard deviation, right? So if you have ever taken a course in visual communication, you see that the error probability on the Gaussian, right, is exactly distance over 2 times sigma, but in this case, the distance is just half this, so we have exactly distance divided by sigma here, right? And so you can write it out. And so the important thing is that now let's do the following here. So let's cancel the n here with the square root of n, right? So then this goes away. On the bottom we have just the constant essentially, and then we have on top square root of n. And so what is this? This is exactly the gap to capacity. So this is exactly the capacity, okay? This would be the capacity, and this is the parameter at which we're transmitting. So let me call this parameter z, okay? So you can see that the error probability is just a function of z divided by some, essentially a constant, okay? Epsilon times 1 minus epsilon doesn't change much. If it just, this product almost doesn't change if I change the epsilon by something very, very small, okay? So what does this mean? If I want now, if I fix the error probability to something, whatever I want, 10 to the minus 3, let's say, and now I want to see what's the relationship between the n and the gap to capacity. So the n is this, and the gap to capacity is this. So what is the relationship such that I get the same probability of error, right? Well, I have to keep z constant, right? As long as I keep z constant, so z simply will tell me what is the error probability that I should get. And then once I have it, this product has to be constant. Is it clear? So the gap to capacity just goes like 1 over the square root of n, okay? So that's what you can do. So if you had a code like this is what you can do. Now, can you actually indeed do this? Yes, if you just pick a random code, just fill in a matrix randomly, then it's just a question of how likely it is that a random square matrix has full rank, okay? Everything over GF2, and I assume that many of you have seen this kind of computation. Turns out if you do a square random matrix and the matrix is not too small, then roughly with 28% it will be full rank, okay? So just take a 10 by 10 matrix, fill in zeros and ones randomly. What's the chance it's full rank? It's this. But okay, so this wouldn't be good enough. But if you just make it one, make it slightly less high than tall, so you're having, let's say, one extra observation or two extra observations, okay? Then every time you do this, the error probability goes down. So if you have k extra observations, the error probability is essentially this, a constant times 2 to the minus, basically the binomial, the binomial of k over 2. So this goes like k squared, right? So this goes down extremely quickly in the extra observations you have. Okay, so this means a random code, it looks exactly what I showed to you. It's not exactly straight down, but the width of what it is just constant. Okay, if this whole thing is n, the width of this transition where it goes from 1 to 0 is just like 1 or 2 or 3, something like this, depending what the error probability you want. Okay, so it goes down extremely quickly, and random codes will exactly behave what I said before. Okay, so now indeed this was the code design, okay, and indeed has been shown, and this goes back actually to a beautiful paper by Strassen. It's written in German, and I think it's actually hard to get a copy of it, and more recently was taken up by some very nice work by Yuri Polyansky, Vince Poor, and Sergei Verdu, and that has to say that indeed what I showed you now for this very trivial example for the binary ratio channel, that's a general phenomenon, okay? In general, optimum codes, okay, you cannot do better than having a relationship that the gap to capacity goes down like 1 over the square root of the block length, and you even know exactly what the constant is. Okay, and it's, they called, in this paper they called it the dispersion. Okay, so we know exactly not just now what the capacity is for code, but we also know how a finite block length code should actually should behave. And so we would like to get close to this, right? That's really our new aim, and that's really something that we would like to do. Okay, so I told you already, optimum codes is n to the, unfortunately it's small n to the minus 1/2. Polar codes, unfortunately, it's like, roughly, this was 1 over that I told you 4 is roughly a quarter here, so unfortunately the block length it needs to be roughly the square, okay, if you don't do anything special. And so now the question is, how do spatially coupled codes behave, okay? And so the upshot is that unless you know something better to do at the boundary, it's not as good as optimum, but it's a little bit better in polar codes. It's pretty much in the middle. Okay, you have a constant. You have a third power here. Okay, n to the minus 1 over third. Okay, and let me just explain in 2 minutes where this comes from. Where does this n to the 1 third comes from? So these are again like plot probability of error curves. For various codes and various lengths. Again, the length improves, and these are 2 different types of codes. And so you can kind of, so this is not a proof, okay, but you can kind of model how the probability of error goes down. And when I mean it's a model, you have to make some assumption, which currently we don't know how to prove. But under this assumption, you can give analytics expression of how the error probability goes down for polar codes, for a spatially coupled one. And essentially, okay, there are 2 terms. One is it's linear, the block error probability in the length of the chain. That makes sense, right? So every time you have the chain, you move over, at some point you might get stuck, right? If the chain is twice as large, it's twice as probable to first order that you get stuck on a chain of twice the length, okay? So that's reasonable. And the important thing is that what you have here is again something that looks pretty much what I wrote down here. So you have e to the minus some constant, then you have a delta squared here, okay? So I forgot the kappa here when I wrote it down here. So this is very good. This looks exactly like optimum codes, but this is not the block length what's up here, right? What's up here is not the block length n, but what's up here is simply that the height that you have in each dimension, right? So remember, the block length is L times n. So where you lose is exactly that up here, this doesn't really matter, okay? The important thing is this. Where you lose is that here is not really the block length up here, okay? So it approaches its threshold very nicely and very quickly, but it's not the block length. So you have, as I said, 2 sources of bounding you away from capacity. The first one is that you have a rate loss, and that we determine is something like 1 over the block length. Okay, so the 1 over the length of the chain, and the constant depends on the construction, and if we're lucky, this is just the constant independent of the degree distribution. Okay, so this is one. And the other one is that what we want to have a certain particular probability of error, and so here the scaling is that in terms of m, right? So what do we need? We need that the gap to capacity that we have in addition because of the finite length effect will behave now like 1 over the square root of m. So we have 2 parts. And so these are written here. So it's the gap to capacity and the rate loss. That's the total thing that bounces away. This one is 1 over L, and this one behaves like 1 over the square root of m But since m and l and n are related, I can write it again in terms of n and l and so on. And so if you look at that, you will see that the best thing to do is to give to l the 1 over the third power of n, and to give to m 1 over 2/3 power of n. So you split the block length that you know, you have the length here and you have the length here, so how to split it. And if you do this, you will see that so far the gap will be like 1 over the 3rd power of the block length. Okay, so on the one hand, you know, so there's still something to be done. Okay, so how could you get better? Essentially, you have to work on the rate loss. Okay, so if you can get the rate loss down to something smaller, how could you do it? Well, either you do continuous encoding, then you actually find, okay, then you don't have this, and you have only the second term, and the second term is fine. If not, you have to somehow find better ways to do to get it started or to get things out at the end. Okay. Good. So this was this. Now, an important other ingredient is that, and that has to do with the encoding part, is that you don't necessarily want in the decoding to work over the whole thing, okay? And so people have looked at that. So rather than when you do the decoding, so this was student Paul Siegel, Armin Iyengar, and some other people that looked at this. So this has to do with how the error probability behaves as a function of the window size. So this is a window size of 4, of 6, of 8. And so what you can prove is, and so this is, I guess, this is the asymptotic performance if the window size is infinity. So you can prove that, again, in the window size, the performance degradation is, again, the loss is, again, exponentially vanishing. So you don't need super large window sizes, okay? So you cannot just decode on one thing. So what does it mean when I do decoding on a window? Maybe I should have first said that. So it means that now, instead of having this whole chain here, what I do is I simply only have a myopic view, okay? I'm only looking at this. Some particular window that I pick. I run, let's say, 10 iterations, okay? And then I move over by exactly 1 position, okay? I don't shift the window over completely, I just move 1 over position, okay? Do 10 iterations, move over 1 position, and then what will happen is there will always 1 new position that moves in and 1 position that moves out. Okay, the one that moves out better be decoded at that point. I'm no longer going to work on it. And the new one, it will just get started. Okay, and so the good news is that you don't need super large window sizes. So the rule of thumb is that this size has to be, like for standard convolutional codes, you know, some small multiple of the connection width that you use. Okay, so maybe use a connection width of 2 or 3. So maybe then you should use, you know, 6, 8 or something like that. For the window decoding, okay? So the effective block length on which you're working really has to do with this, because that will determine the delay and everything. Okay, so I think we can just skip that. So so these are just various references for, you know, people that have looked at that. Okay, so any questions to these topics? Now I want to go back to the characterization of the threshold, and I'm not going to really do, let's say, any proof, but I'll just tell you a little bit, you know, how you might show that this indeed happens. So before we go on, any questions about, you know, these aspects that I talked about? Yes.
What exactly is the benefit from the inputs?
What exactly is the
Benefit.
So there are 2, right? One is, right now, everything I did was flooding schedule, parallel flooding schedule, right? So maybe you have a length 100 here, and you're simply running, you know, you're churning a wave, right? But what you have seen is when you have the wave, right, that really all the action is happening where the wave is, right? The wave has essentially finite extent, and in the middle, nothing is happening, right? So it's just a huge waste in terms of computation and energy to do computation where you're basically stuck in a fixed point, and you know, you're saying, you know, is there any no information? No, there's no information. Is there any new information? No, there's no. Okay, so you will only really have to work on the part where actually the wave is just making the transition between this fixed point that you had and the desired fixed point, which is where you want to decode. Okay, so one is energy consumption, you know, reduction in just computational power, and the other one is that now you can start reading off the bits as soon as you move over the window by 1, right? And so now you could actually do a continuous encoding or just start already using the bits. You don't have to wait for the whole thing to be done. Okay? And also in memory, you know, whatever you're working on, you're just working on that, right? So it could be a huge reduction in memory because you're only working on that window. And that might actually be one of the most important aspects. Sorry? No. So there's simply a loss. So the wave, strictly speaking, extends, of course, over the whole thing, okay? But it exponentially fast approaches the two basic states. So because of that, the essential... Yeah, so there's a window size where you essentially have the whole wave in there. And then there's still the little bit gap that, there would be, once in a while, there would be a message that comes from the right to left, but that probability vanishes exponentially fast in how fast you go. And so basically that doesn't help you, okay, for the leftmost bit. Good. Good, yes? So if the wave, okay, so if you have wave in two sides, you can do what, okay, so if you do decoding, of course the wave will only work where you're actually working on, right? So, it depends on what you want to do. Okay, and there are all kinds of advantage. So what might be advantage, for example, to have the wave in two sides? Just to tell you, so far we have talked about everything two-dimensional, but you could do the same thing, for example, on a grid. Right, you can do this in D dimension. So you could simply imagine that you have a grid. Okay, let's call it a lattice. Okay, to make connections. Okay, and then you have a grid, and you could imagine that at every point here you have actually a code sitting. And now these codes could connect in exactly the same way they have, but they could be in 2 dimensions, right, or in 3 dimensions. And so now, we are very similar to this situation here. You could simply now, think of this maybe as a torus or, whatever, how you want to wrap this around. And now maybe you start here. Maybe you give me these 4 positions bits to be known. Okay, so these are now known. And this is now your seed. And now it will start growing out from there. Okay, so you could do this in several dimensions. Now, why do I bring this up? So far, we have not found a problem in which the threshold saturation occurs doesn't occur in this one-dimensional case, but would occur in this higher dimensional case, right? So there doesn't seem to be much, benefit to go to higher thing, right? I'm not just talking about coding. You can do the same thing for compressive sensing, for problems in statistical physics, for KSAT, etc. So there doesn't seem motivation, but and the boundary problem becomes worse. So kind of the amount, the code length that you need now, imagine that you have this now in 2 or 3D. The code size, of course, increases, right? So that seems to be bad, right? You don't want the whole code size to increase, right? So what could be an advantage? The advantage could be is that in a one dimension, and if I only start from a single part, right? If at some point I get stuck because the channel is atypical, I'm stuck. That's it. Okay? Maybe I have feedback, I can restart or something. But if I don't have anything, I get stuck. But think of it in 2 dimensions. Let's assume locally here, I have maybe a little bit more noise than usual, okay? I have now, I can now approach from here, I can approach from here, and from here, right? And so I don't have a single path in which I might get stuck, right? And indeed, you can actually check that the error probabilities that you get might actually become much better, okay? Because the probability of getting stuck, if you think in terms of the scaling laws, is much smaller, so there could be some benefit, okay? And so now you have to balance the benefits against the whatever it costs you to do that. So it's not so clear. Okay, so now there are in principle 3 ways so far that people have both analyzed or also characterized these threshold saturation phenomena. And depending, what is your background, some might be much more natural than some other ones. Okay, so I will not go through all of them, but I just want to point out that there are 3. If anyone knows exit charts, has anyone seen Stefan Tambring's exit charts? No one? Okay. Okay. Sasha. Okay. Okay, so this is some characterization of iterative decoder that works typically when the decoder is one-dimensional. If you know it, okay, so this is the typical picture, then there's a very beautiful, it's basically exactly the same picture with a slightly different criteria. But since nobody ever heard of it here, okay, I'm not going to mention it because otherwise I'll spend half an hour to first explain what this picture is, okay? So this is a very, very useful characterization if you know this picture, okay? So if you ever come across exit chart, something very useful, and then this picture is basically automatic. It's very nice and very simple, okay? So there is the first one here by the Maxwell one. I'll talk to you a little bit about it. And so this is the historical first one to see, and that's the one that you see the connection to the map threshold, okay? But there's a third one, and it's mostly due to Henry Pfister and many of his collaborators that have been worked out, and that's currently the simplest way to see it, and that's with potential functions, okay? So if you maybe want to see a first proof, that doesn't give you that this threshold is the map threshold, but it gives you the same threshold. It proves that this is the threshold, but doesn't show that it's the map threshold. But this is, I think, by far the easiest proof to follow, okay? And so, all of them have their benefits. It's also something that if you maybe have a more physics background, that uses what's called potential function. It's very natural from that perspective, okay? So it really depends what your background is, what is easy and what is not. Okay, so let me look at first the characterization at the most on the left. And as I said, this goes back to this work with Cyril, who was a student at EFL some years ago, who did this Maxwell characterization. And then this is joint work with Srinivas and Tom Richardson. Okay, so let's go back to our trusted curve. Okay, so we have our nice exit curve. Confusing enough, this is also called exit curve, but has nothing to do with this exit chart, or very little to do with this exit chart that I talked about before. So, okay, so we have this, remember, this is the channel parameter, basically something like error probability or exit parameter, and depending where I am in the code, this is the threshold here. Fine. Okay, so we've seen that in this curve, the BP threshold of the uncoupled one is very easy to see, but what I want to show you that inside, in this curve, is also already encoded the BP threshold of the coupled. Okay, so we have seen the BP threshold of the uncoupled one. I show you that now in terms of the curve, you also see the BP threshold of the coupled. And how do you see the BP threshold of the coupled? You see it in the following way. You look at this curve, okay, and then you simply integrate from the right until to the point where this area here under the curve is exactly equal to the rate of the code. Okay, so there's a unique point. So just draw a line somewhere here, a vertical line. At some point, this area here will be equal to the rate of this code. In this case, it's a half. Exactly this point that you see here, that's this threshold that we're talking about, right? So that's the 0.4884, whatever, for the 3.6 code. And that's the 0.43 for the thing. And since this is determined by an area, okay, this threshold is called the area threshold. And it just turns out in hindsight that that's equal to the map threshold of the underlying one. Okay, so it just turns out that they're all the same. Okay, so that's the characterization of this threshold. So this is how you can compute it. Okay, so I showed you before, and at least for the BC, how you can very easily compute this curve. There was a trivial characterization of this curve, right? It had just some parametric form. Now you just integrate this out, find the point. This you can solve explicitly. You get the threshold. Okay, so this is the characterization. Of course, it doesn't necessarily tell you what why this happens, but it tells you where it happens. Okay, so now we want to get to why this actually happens. Okay, and so we only need essentially one ingredient, and then with hand waving we can essentially see how we can do it, and that's the following. Remember, the real exit curve that we had, the whole one with all the stable and unstable fixed point, had this C-shaped curve. Okay, so this C-shaped curve had an explicit characterization. There was this parameterization that I told you. Remember the epsilon is a function of x, and then this is the exit value. So this curve we know explicitly, right? And so what you can do is you can simply compute the area inside in here. Okay, so it's just a calculation. You can compute it. You don't know why, but we can compute it. And so, this is just some fairly simple calculation that you have to do, and it turns out that miraculously, this area inside is also equal to the rate of the code. Okay, so and that now is something fundamental. Okay, it turns out that any time, whenever you have a curve like this, okay, so what do I mean like a curve like this? Every point here is a fixed point of dense evolution. Okay, so this is a nice smooth curve such that every point on the curve is a fixed point of dense evolution, and that starts here basically at the useless case and goes down essentially where the error probability is 0. Okay, so as I told you, for the regular case, these are very nice, but these curves could look anything crazy. It could be anything. Okay, but no matter, anytime you have such a curve, such an exit curve as I call you, made out of fixed points of dense evolution, the area that's enclosed is always equal to the rate. Okay, that's it. Okay, now here we could do an explicit calculation, but it turns out that you can do a conceptual proof. You don't need to know what the curve is. You can just say, because it consists of fixed point and it's a nice one-dimensional smooth curve, the area enclosed must be equal to the rate. Okay, so let's take that as a fact. Okay, and so this is also true for spatially coupled. There's nothing says what kind of code this is. It's also true for spatially coupled. Okay, so now the idea will be the following. Okay, the idea will be of the proof will be the following. So this is again my box that I always draw. So this is, let's say, the positive, this exit curve just including the stable fixed points. And so now the idea will be the following. The idea will be to show that I can construct an exit curve for the coupled case, which looks like this. On top here, it's equal to the exit curve of the uncoupled one, and at some point it will drop. Okay, I don't know where it will drop, but at some point it will drop. And what does it mean that I construct such a curve? What it means is that I show you that there are points like that correspond to these points, and every such point here will be a fixed point of dense evolution for the coupled case. That's all it means. That's exactly what it means for the uncoupled case. Each such point corresponds to a fixed point. Okay, so if I can construct to you a curve like this, what, I can already give you now the, what will be the point. The point will be is that a priori when I construct to you, I don't know where this point is. Okay, I just know that it's like this, and then at some point it will drop. But remember, this whole thing will be an exit curve, and if it's an exit curve, this thing here the area must be equal to the rate. Okay, but the top part is equal to the uncoupled thing, and what did we call this point here where this area is equal to the rate? We call it the area threshold. Okay, so this will prove that this point here where we're getting must be exactly the area threshold, and then there's just some point to prove that indeed this exit curve has an operational meaning that if I have that, it means that below actually it must be decoded. Okay, so this will be the 2 points that I want to do. I first want to show that there are fixed points which correspond to it. I get an exit curve. I know now what this point is. It's the area threshold. And then finally I need to show you that indeed if I go below, that there's some operational meaning to it, right? Because maybe it's just some construction, but who tells me that this exit curve actually has some meaning? Okay, so let me just tell you quickly of how you construct this, this curve here, and then we basically finish. Okay, so how do you do this? Well, so I need to give you now points which correspond to these points here. And so remember, these were these density evolution equations that I have. And so I'm asking now, what are non-trivial fixed points of this density evolution operator here, right? So I need to find constellations. And now it's more complicated. A fixed point is not a number, but a fixed point is actually a function, right? For every point, I need to give you something. And so, so the way we'll go is like as follows, okay? The only thing that I need to show to you is that there is a fixed point that has a shape like this. And what do I mean with shape like this? It should be flat here, okay? It should be essentially 0 towards the boundary. And this transition should not be too long. I mean, it should just be something that doesn't take up the whole space, okay? It shouldn't just be that it just goes, at basically 0 slope, okay? I claim to you that if I can prove to you that there is a fixed point of dense evolution for a spatially coupled code that looks like this, then I'm done, okay? And so why is that true? Well, so the first thing is I need to show you that I have such a fixed point. And then I need to show to you that from this single fixed point, I can construct all the fixed points that you have here. And then I need to show to you that indeed this gives me the desired result. So to show that there's a fixed point, that I will skip, what is it, right? You have an operator, right? And so you have this map here. And I need to show you that there's a fixed point of this map. Well, how does one show fixed points? One standard technique to show fixed points is some fixed point theorems. Okay, so there are many of them. The one we'll use is what's called the Schauder fixed point theorem, but there are many other versions of such fixed point theorems. Okay, I just need to show you there's a fixed point of this map, and I need to show that this fixed point has some properties which you somehow need to encode in the map that's in there. Okay, now this is kind of the most technical part, but it's a standard technique that people have used that there's such a fixed point. So let's assume we believe that there exists such a fixed point. Okay, I don't know anything else. I don't know how high this is. I don't really know the shape of it. The only thing I know is that it's basically 0 here, basically constant here, and then we can assume here symmetry, and that these transitions are not too slow. That's the only thing, and it should be a unimodal function. That's the only thing I know at the moment. Okay, so now out of this fixed point, okay, how do I show to you now that I have all these other fixed points that I have? Okay, so I claim that that's actually fairly easy to do. Why? Okay, so let's take the fixed point that we have, okay, and let's assume we cut it somewhere. Okay, so we cut it wherever it is already basically flat, right? Well, if I cut it somewhere here, then what I can also do is, so this point here must be some point on this curve here, okay? So I don't know exactly where it is, but it must correspond. This is one fixed point and will give me somewhere a point, okay? But how can I construct other fixed points? Well, I can easily construct some other fixed points. All I need to do is that in the part where it's constant, I can shift in some extra constant terms. Is that clear? So if you believe that this thing is exactly constant on top, if I'm adding another point in here, right, And if this is large compared to the connectivity width, then by dense evolution, this will be still a fixed point, right? Because it's just a constant. Now, we don't know that it's exactly a fixed point, but it actually turns out that for the argument, all we need is that it's essentially a fixed point, okay? So it doesn't have to be exactly a fixed point, it just has to be close to a fixed point. So it's enough that this is almost flat up here, and that's what we have. So, but what will happen if I have another such fixed point here? Well, I just make this larger and larger, and what will happen is that these will all be fixed points, okay? And I can do arbitrarily many, I can do a whole curve here, and they all will correspond to fixed points for the same channel parameter, okay? So I don't know what the channel parameter is that corresponds to the original one, but all these fixed points here all will correspond to the same channel parameter, right? Because it's all the same recursion, everything. So this must be something that goes up from essentially something very small to essentially up here. Okay, now, so this gives it, and then once I go up, I need to show that I can still complete this curve up here. That's a slightly different argument. I'm just going up. Essentially, I just take a constant. I don't know it to be exactly a fixed point. I just need it to be approximately a fixed point. Now I have basically a whole curve. I interpolate them so that I get a whole curve. I know that the area in here should be exactly equal to the rate if this was an exact set of fixed points. I know that it's almost equal to the rate if it's almost equal to fixed points. I put all the epsilon deltas in here, and because of that, I know that this must be exactly the area threshold. Okay, and so that's essentially the proof. And so the final one, which I'll skip here now, is just to show that this has an operational meaning. And so this means that, that if I'm, again, the same thing appears, that if I'm starting with this and I have an error probability which is slightly better than, a channel parameter which is slightly better than one for which the fixed point exists, then indeed it must decode. Okay, so that's the basic idea of this. And so indeed this is how we originally did it. And it turns out that because, so here's another nice way about spatial coupling. It turns out that you can't just use spatial coupling to prove things about the spatially coupled codes, but you can actually use it to prove things about the uncoupled one. So now where we know that this area threshold, okay, is equal to the the decoding threshold for the spatially coupled, with a few extra parameters, okay, or a few extra steps, you can actually show, and this was done by another student, it's this paper, Andrei Giurgiu and Nicolas Makris, that you can show that also the uncoupled code indeed has, its threshold, its map threshold is equal also to this area threshold, and that they're all the same, okay? So actually this is the only proof we know how to prove that in the general case, the map threshold of the uncoupled code is equal to this area threshold. There's no standard technique that I know, information theoretic technique that would allow us to prove this. And so that's kind of nice. Okay, so here we have used spatial coupling not to show something about the spatially coupled code, not as an algorithmic tool, but we have actually used it to prove something about the underlying system of the uncoupled code. Okay, so that's a nice benefit. Okay, now let me just say a few words about this nice potential function approach. And so, as I said, this is, at least in a one-dimensional case, like for BEC or some other systems, it's by far the easiest way to get there. By far the easiest once you understood what potential functions, so it's like modulo, of course, something, but it's a very nice way, and the proofs are simple, and I think it's a very elegant way of doing it. Okay, so everything here will be for the BEC, okay, and so it's just the last 5 minutes, so, okay, let's see how it goes, okay? So the first thing is you define a potential function. So there's the channel parameter in here, and everything is BEC. This will be again the x, always the x that we always had around, okay? And so how is this potential function defined? It's an integral, okay? It's an integral of a function. Now, so what are these functions that I have in here? That's a little bit difficult to see right now because I've never talked about the irregular case, but it's actually all quantities that we know. It's just that we didn't call them like this. So it's the integral from 0 to x. And the first one is z minus, and I had called it actually f of epsilon and x. Okay, so I call it like this, so of z, and then there's still the rho prime, and the rho prime. So what is it? The rho prime of 1 minus z. But what is the rho prime? The rho prime just is the degree distribution. So for us, the rho prime is just the rho of x would just be x to the, for our case, x to the r minus 1, okay? So for us, the rho prime simply is r minus 1 times x to the r minus 2. And then since I have 1 minus c, all this thing here it's just something explicit depends on the degree distribution. So it's r minus 1 times 1 minus z to the r minus 2. Okay, that's it. So what are the parameters? This is something, simply an increasing function. Okay, so sorry, it's simply a non-negative function here. Okay, so this is the only thing that we need, that this is non-negative here. And what is this thing here? This is exactly dense evolution. So this is simply the state of the system at some point. Okay, so if we are in state z here, we do one more iteration, this is what we get. Remember, I had called it f. Okay, so this is simply the progress that we're making. Okay, so that's it, and you integrate that. Okay, no idea why you would start with this, but let's assume you do. Okay, so the claim is that this is a very nice function, a potential function, and so the claim is that you can trivially see in this potential function first the BP threshold of the uncoupled system. How do you see it? Well, so this is the okay. So this is the is this, yes? Let me just see where I am. So this is, what are these different functions here? These are this potential function for different epsilon. So this is the epsilon, a large epsilon, and this is this is a small epsilon, and the epsilon is increasing. So let's look at this. This is non-negative, okay? And as long as this thing here is also non-negative, okay, then since I'm integrating over a non-negative function, this will be an increasing function in x, right? So if it's an increasing function x, this is like something like this. This is an increasing function of x, right? So this is always non-negative. When is this increasing? This is increasing if at every point z, you're actually making progress. At every point z, you're going down, then this thing here will be non-negative. So as long as the iterative decoder works everywhere, this thing will be increasing. So how do we see the BP threshold in there? Well, we simply look at what will happen if at some point actually this thing, if this will actually be stuck, then we're looking at a point where at some point this is actually no longer strictly increasing, it's just flat. Okay, if we have at some point 0 there, then this, if I'm integrating at this point, it will no longer be increasing. So where does this happen? It happens exactly here. Okay, so this is epsilon 0.4, and now you do exactly at the threshold, you see that this is the first time this curve becomes flat. So you see actually the BP threshold in there. And the claim is that you see also the BP threshold, the coupled one in there, exactly at the first time, this, the kind of the minimum of this curve here is actually 0. Okay, so it's basically exactly the potential function. You should think of this difference here as a kind of like an energy term here. And as long as the best solution that you can find locally here has an energy which is strictly above the desired fixed point, which is the energy here in this thing 0, then you will actually converge to this. But if this turns out to be ever smaller, then the optimum solution is actually here, and you will no longer converge to this fixed point. Okay? So this is essentially the interpretation for this. So this is exactly the same characterization of the area threshold. And so you can also make a proof like this. I think I'll not go over this. It's not super complicated. Okay? It basically uses just the Taylor series expansion of this potential function. You need to compute the first and second order term. You need to show that the first order term is the one that dominates, and that's essentially the proof. But since everything is multidimensional, I'll just show it to you. That's the proof. Okay, so that was the proof. Okay, so but it's it's worth looking at it. I think it's it's quite a little bit simpler than the previous proofs. Once you put all the epsilon deltas in there, it shows the same kind of result. Okay, so forget about this. And so let's just go back now to our final slide here. So that's basically the end of what I wanted to say. Spatially coupled codes. So we said that they achieve capacity. That's nice. We said that the block length scales like 1 over delta to the third power. And then you can also look at other things, encoding complexity, decoding complexity, etc., etc. And in particular, one of the nice things that they have is that they're universal, and that can be quite important for various applications. Let's assume you don't know the channel or something like this. And also you can use the same principle, so compressive sensing I mentioned. You can use the same principle for some other constraint satisfaction problems like KSAT and so on. And so it's, I think, like an interesting technique. Okay, thank you very much. Yeah, I don't know if there's any question, otherwise, yes?
What are the properties of the EEC channel that allow you to prove the EMA or the E area?
So this is true in general. It's not just true for the BEC. Okay, so all these the proof also works for the general case. And all these things I told you are true in general, except that it's no longer now one-dimensional things and it's no longer simple integrals. But if you generalize it properly, this is all true. So there's an exit function for the Gaussian case, and whatever, if you have an exit curve like this, its area must be equal to the rate of the code. All these things are true in general. Okay.
What's the potential function also?
The potential function approach can also be a thing, but then you can imagine that it's no longer so easy because it's, again, not just a one-dimensional integral. You're now an integral in some large space. So you first have to even prove there's not just a single path. You have to prove even that no matter how you integrate, right, that it's really a path integral, right? So there's something to do with the field that you're integrating over that you need to show that this is indeed a potential function. Yes?
Yeah, just a question about, so when you say the block length is 1 over delta cubed or delta metric, is that mostly from experiments or is there some theoretical?
No, this is what I had beforehand. So I had this discussion where I said that there are two losses. One is the rate loss and the other one is the actual finite length scaling. And if you look at how you have to choose the parameters, it comes out that this is 1 over delta third. Okay. So now when I say that this goes like this, so this is the rate loss is clear. It's like this. Okay. For the other part, that's the best one we right now know for this rate loss. Okay. So it could be that it can do better by getting rid of the rate loss, but right now we don't know anything better. Okay.
You're saying universal. It doesn't mean that the device is fixed and it does not know the transitions.
So okay, it's universal in the following sense. Okay, that the code is universal. Okay, and now so this means that if you once construct the code, let's say the family is all the binary input memory symmetric channels. You don't know which one beforehand. Okay, you fix with fixed capacity or thing. And then this code is universal. Now, if you want it also to be universal with respect to that, even at the decoder you don't know it, so this assumes right now that you know, then you have to do more, right? So in principle, you can do it. You just need to split the space into many decoders, try them all out, and then take the optimum. Complexity-wise, would be quite horrible. But I think in practice, that's maybe not the most important right now. What's important is the code itself, okay? Assuming that at the decoder, you can convert the log likelihoods in the proper way, so that at the decoder, you assume that you know what the channel is. Okay. Yes, Chandra.
Is there some way to get the rate from the potential function? You got leaking thresholds and the math threshold from the potential functions. I mean, first way where especially going to first way where it was zero. First we do the potential function both ways, and from the curve you could get the dB threshold and the math threshold.
Right.
Is there some way to get the rate? Like this is an linear theorem equivalent from the potential function. There's something when you get back the rate.
If there's something, it's hard physically to understand. If there's something,
can you get the range of the code from looking at just the curve?
yes, because it's equal to the rate. So if you integrate the area is equal to the rate,
so
right?
Which means that the internal function, there's some incremental rate limitation of what you're integrating. So you're integrating some function, right?
Right.
Is there some interpretation in terms of
Yes. So if you integrate along the curve, what you're doing, you're computing the conditional entropy. Okay, so at any point in time, you know what h of y given what h of x given y is. Okay, so that's the interpretation of this curve. Okay, and that's indeed how also the proof then goes that that's the math threshold.
Continuous encoding and means of encoding, you get optimal scaling. What length of the?
You're saying if you do encoding, yes. So I think more or less, okay, so there's still something for any fixed degree, right? There's still the threshold is not exactly capacity, right? So you get optimum scaling to its threshold, but that's of course not the scaling to capacity. So if you wanted to do a real scaling, you would have to increase slowly the degrees and slowly the block length and do it. And so there might be some extra log factors that come in there or something like that, okay? So you would have to check exactly how this works out. Right? Because the threshold for any fixed finite degree, you never have exactly capacity, right? So if you look at a sequence of codes, you have to also let the degrees grow because even a map, any map, any code that has finite fixed degree, but there's a Gallagher bound that bounds it away from capacity. It's very small. It's like double exponentially small away, but there's some gap. Okay. Okay. Thank you very much then. Okay.